Okay, so let's get started. NumPy and Matplotlib. So, as I said, kind of NumPy fundamental package for scientific computing, working with arrays like you maybe kind of like vectors, matrices, and so on in many different dimensions, doing linear algebra and doing computations. There are functions for making sine, cosine, to square numbers, and so on and so forth. And then Matplotlib is one way, or kind of, I guess, the oldest and most popular library for plotting and creating visualizations in Python from within Python. There are several other packages that allow you to visualize things in Python. And towards the end of the course, we're actually going to look into interactive or packages that allow you to do interactive visualizations. So the main takeaway for Matplotlib is that these are kind of just images and they don't allow interaction. As before, if you have already set up your Conda environments or an alternative setup, you can use those locally. If you don't have, no worries, you can still go to Google Colab and follow along in this tutorial. So the first thing that you will have to use, so maybe we should start earlier. What is a package? What is a Python package? You can think of it a bit as an add-on or a plugin for the basics of Python. So these are people, they are all open source. There are different communities. There are volunteers, sometimes also paid people who develop these libraries that offer specific functionality in Python. And they are kind of packaged in so-called packages or libraries, such as NumPy or Matplotlib, that then need to be imported if you want to use them. So one prerequisite is, first of all, that you need to have these packages installed in your environments. So they do not come with a basic installation of Python. And then the second prerequisite in the script that you are using it in, it's a good style to do it at the top, but you can also in principle do it anywhere. But in any case, before using functionality of this package, you need to import it. And sometimes the names can be lengthy, especially if you would be typing it multiple times. So they are often imported under an alias. And the command structure looks like this, that you kind of import NumPy, import one of our packages under an as, so as an alias np. It's kind of just an abbreviation that we can use later as a shorthand. And whenever we refer to functionality offered through this library, we can reference it through this alias. Same goes for Matplotlib. You can also import, so Python packages might be organized in so-called modules, kind of substructures of the package itself, for example, pyplot, and those we can also import under specific names. For example, Matplotlib pyplot as plt. And these are just kind of common abbreviations that the broader community kind of has agreed on. So let's go with NumPy first. And the core data structure for NumPy are the so-called NDArrays. ND stands for n-dimensional, so it can be arrays that can have 1 dimension, 2 dimensions, 3 dimensions, or n dimensions. And it's a data structure that is made to allow really fast computations for larger arrays and matrices on numerical data. But in simple terms, it's kind of like a list in n dimensions. So last week we learned about Python lists. Python lists have some disadvantages in terms of performance for large arrays. So this is kind of where the NumPy ND array comes in. And there are a few main differences between a NumPy array and a list that, well, NumPy NDArrays can have n dimensions, whereas lists can only have one dimension. You may be able to kind of formulate lists in lists. That's also fine, but then it doesn't have like really well-defined meaning. And what is also the case in lists is that you can fill it with several different data types. Like your list could consist of an integer, a string, and a floating point number. Whereas in NumPy, you're really restricted to numeric values, and they always have the same data type. They can be integer or a floating point or some other numeric data type. So if you have, for example, a data set like this 2D data set here, you maybe have actually an integer 3 here, but because you have other floating point numbers, decimal numbers, this will also show up as a floating point number. So you have a consistent data type for every element in this object. And then there are several different functions available that allow you to do mathematical computations fast and efficiently. So what you get out of an NDArray is not just the values that you can access in principle in similar ways as in lists. You remember maybe the square brackets that we used several times last week. But you get also some meta information about the shape. So the kind of how many entries along the different dimensions. For example, this 2D array along axis 0, dimension 0, has 2 entries and then 3 entries across. So that's the second value here. So how do we create NumPy arrays? There's several different methods, but for example, one of them is the NPArray function, where we can, for example, put in a list, and what we get out is kind of something that is of type array, but otherwise looks pretty much like a list. And if we want it to be 2-dimensional, we could call this function with kind of 2 lists inside each other. So this list inside and this list inside an outer list. And these are all integer values, but in constructing the array, we can also explicitly specify what the D type should be. For example, NumPy float 64. Just a specific type, and the number here refers to kind of how big the values can get. And then it looks like this. Reorganizes the data a little bit and shows it as kind of 2D array. Okay, so the information that we can, 2 key properties that we can access from a NumPy array is, first of all, what is the data type? So for A, we only had integer values, so the D type here would be int 64, and the shape here for A would be 5. We only have 1 dimension with 5 entries in this data set here. We can do the same for B, data type as we specified, float 64, and the dimension is 2 along axis 0, 4 entries along axis 1. Remember, in Python, we count from 0, can be confusing at the start. There are several other ways to create arrays. For example, we maybe want to prefill. So maybe we know our array that we're going to create is going to have a lot of 0 values, and only kind of some distinct values have some non-zero values. Then one way could be to say we want to create an array of zeros with a size 4 by 4, and get this 4 by 4 array, which we can then kind of change some of the pre-computed values. We can also do this with ones, and we can do that also in 3 dimensions. So here it also already gets a bit complicated to look at what data is actually stored, but this would be a NumPy array with 3 dimensions and 2 by 2 by 3 size. And if we don't want it to be filled with 1, we can also call it with call the full methods, and say we want a full array with this value np pi. So this is already kind of one attribute that we can access from NumPy. It's just the value of pi. I think we can also access the value of e, for example. Just a kind of small utility, but it doesn't exist in basic Python. There are ways to do it with random numbers. These random numbers would give you just uniformly distributed random values between 0 and 1. And then there's this NPArrange function, which would give you kind of just a list of values. It's a bit like the range function that we used last time, that would just count from 0 to the 10th value, which in this case would be 9. What we cannot do with range, what we can do with NumPy-arrange is that we can define a certain step size. We can, for example, say go from 2 to 4 in steps of 0.25. And then we get a kind of a list or an array, a one-dimensional arrays values from 2 to 3.75. So 3.75, maybe, oh, it sounds unintuitive. We said we wanted from 2 to 4. But this is one of the aspects that is important to remember for the arrange, is that this value, this kind of n value, is not inclusive. Yeah, so if we put 0, we could say 4.01, and we would get the 4 in there. Yeah. What also sometimes may be useful is to say, I mean, here we specify a step size, but maybe sometimes we don't know the step size, but we have an idea of how many values should be between two values. For example, there we could use the function linspace, which returns an evenly spaced set of values within a given interval. And yeah, so depending on your setup in Python, in your coding environment, you can access these doc strings, so-called doc strings. So these doc strings are just the documentation that the packages provides. It gives you kind of the name of the function and explains all the different arguments that you can give to it. So I set it up that if I kind of hover over a function, I get this string. But maybe if you're in Jupyter, for example, one thing that you can always do for any function is you can say n.linspace and then add a question mark, and that will print the docstring in a text format. That's one way to access the documentation. Or you just go look for NumPy linspace documentation. Usually it's the first, and this is the exact same information. Sometimes you need to be careful about kind of what version this documentation is for. So for example, it says here, this documentation is for an unstable development version. Maybe I should switch to the stable version or whatever version I have just installed. Okay, so this is useful, and in the assignments sometimes also expected to kind of familiarize yourself with new functions that we didn't talk about before. But so now what happens if I execute this function? I get kind of a set of 21 values between 2 and 4. And in this case, the 4 is included. What would it look like if I set 20? Then I would get kind of uneven, non-integer values. If I want 20 values here, or 21 values, then I get kind of both the 2 and the 4 inside as well. Okay, so about indexing and slicing, it works pretty much the same as dictionaries or lists. You can access them with square brackets, and if you have multiple dimensions, you just separate by a comma. So this would give you the second entry in the first dimension and the third entry in the second dimension. So the 3. So let's just go back up to the definition of B. So the first entry in the first dimension. Sorry, the second entry in the first dimension. So that would refer to our second list. And the index 2, so the third entry in this list, the inner list is our second dimension. That would be then this value of 3. Okay. If we want to get a specific row, we can just kind of say we want the first row by just not specifying the second dimension. And we can get a specific column of B by saying we want maybe the fourth column. So index 3 could say we want from all the rows indicated by the colon, we want the fourth entry. And that would then give us 9 and 0, which if you look back to B would be just the final column. You can also do this slicing where you say, I want all values from 0 to index 2, both for the rows and the column, and you get kind of a subset of the array. Okay, so the key reason why NumPy exists is that you can do so-called vectorized operations, meaning that if you want to do the same operation for multiple entries or all entries in a NumPy array or a list, you don't need to iterate over it manually. You can just say, well, it's kind of linear algebra. You have your array B, you want to multiply all its value by 2, so you get all of these values multiplied. And say you have another array C of the same shape, then you can also just say B plus C, and it will add up kind of element-wise these values without the need kind of to iterate over the indices. And this does not just work for kind of basic plus minus kind of basic math operators, but then there's a range of different functions like sine or cosine that then allows you to quickly calculate that element-wise as well. So I brought kind of one example to illustrate why this vectorization makes a lot of sense. So the example here is we want to square we want to create a list of the first 100 million values squared. And everything around this is just some form of kind of keeping time. So there's another package called time, which just gives me kind of the time at the beginning of code I want to execute, and then I can log it again. And then at the end, it gives me the seconds that are between the start and the end. So this is kind of the naive implementation that just kind of iterates over the first 100 million numbers. And you can see maybe when I tested it was 4 seconds. Yes, so that takes 4 seconds. But if I use NumPy and I do exactly the same thing, I just log the start and the end, but I create kind of, first I create this array of the first 100 million million numbers, and then square that. That's the vectorized operation. That took just 0.15 seconds. So code can be much faster if you do vectorized operations, if it's kind of the same operation for many elements in kind of an array. Okay, so another cool concept, and that's maybe a bit more complicated, or maybe creates a knot in your head. It's so-called broadcasting. So so far, when we did, for example, the summation b plus c, both of the arrays had exactly the same dimension. But with broadcasting, we don't need the two arrays that we want to process. We don't need them to have exactly the same dimensions. They can also be, they only have to match in some dimensions. So they take this example here. Maybe let's go with the first one. So this is the example we had before. We have two arrays with exactly the same dimensions. But now assume that actually we only have kind of three entries, a one-dimensional NumPy array that we want to add to this other 3x4 dimensional array. And what NumPy does implicitly, it checks the dimensions. Do some of the dimensions align? And if only one of them does not align, then it will kind of broadcast. It will kind of stretch the array, kind of stretch the same kind of stretch the column values across the different rows of the other NumPy array to get to exactly the same result. And in fact, we could also just have kind of one array that has dimension kind of size 1 in one direction and 4 in the other, and then kind of one that has dimension size 3 in the first dimension and 1 in the other, would do exactly the same thing. Could stretch the first one along the columns and the other one across the rows, and what you get in the end is exactly the same result again. So broadcasting just kind of, depending on how the dimensions line up, just stretches your arrays, and that can sometimes be useful. So here's an example. We have this array of kind of size 4 with one dimension, and we have this, we don't have this. We have this b with dimension 2x4. And if we now do b plus d, we can still add these values together. And it does exactly kind of this step here, extending the rows. So kind of each of these rows, we add 10 to the first column, 20 to the second column, 30 to the third column, and 40 to the fourth. So you can show up the rules. You can look up the rules, what they are. But basically, two dimensions are compatible if they are equal or one of them is 1. And the dimensions, the way you will see that dimensions are not compatible is you would see so-called value error being raised. So take this example of x and y. So x is kind of 3, so x shape is 3x4, y shape is 4. So each dimension's last index aligns and the first one doesn't. So this works, x plus y. And here's another example that does not work, where x.shape is 3x4 dimension, and y shape is 3. So you would say maybe the way I explained it, this should still work, but it actually doesn't, because NumPy compares the dimensions for compatibility always from the last dimension. So if this one has its last dimension 4, and this one has last dimension 3. So that means if these values are not equal, then these shapes are not compatible. So if I do x plus y, I will get this value operate. You could say the operands could not be broadcasted together with these shapes. I can transpose, just the kind of swapping the dimensions so that I have 4 by 3 and another one with size 3. Oh, sorry. So I could say x equals xt. So I override that so that my shape of, sorry, not what I wanted. So that my shape is 4 by 3. So now the size of the last dimensions align, and my x plus y works. Yeah, so the key takeaway here for broadcasting, the sizes of the last dimensions have to match, and if one of them has a smaller dimension, then this is basically ignored. Then it's just assumed that it's the last dimension, kind of this dimension here, which is size 4 in x, does not exist in y. So then this dimension is broadcasted, but nothing else, because it doesn't have information about how to do it. Okay, so that's one thing out of the way. One other thing that we have we have big NumPy arrays. There's a lot of different information. It's kind of hard to see. Each row stands maybe for a country or a location in general, and the columns stand for a different type of power plant. We maybe want to do some reduction. We maybe want to build a sum or something, a sum, find out something about the minimum, the mean, max, or the standard deviation. Then take our array B from the beginning. We can call functions like bSum, which would sum up across all the dimensions, which would give us a value 30 a scalar value of 32. But we can also specify a so-called axis. Axis is kind of a synonym to dimension. You can say axis 1 means we want to calculate the mean across each of the rows. So that would give us kind of the average of the first row and the second row, or the mean of each column. So that would give us 7, 2.5, 2, and 4.5. Yeah. So kind of the direction of the averaging function also matters. And then sometimes we maybe want to select parts of an array based on some conditions. For example, all the values where the value exceeds a certain other value. So in this example here, let's say we have a values array of kind of 10, 20, 30, 40, 50, and we want to select all the values that have a value greater than 25. So if I run this, I can kind of do this check, values greater 25, and this will create this mask object, which has kind of true wherever this is the case. So for the last 3 values in this list, but for the first 2, it's not the case. And this mask I can use a bit like we use kind of accessing values in a NumPy array through the square brackets by the number. I can also pass a list of true, false values, which would then give us kind of a reduced data set that only has those values that meet the conditions of the mask. Okay. So basic plotting with Matplotlib. So especially for larger arrays, kind of it becomes quickly hard to see. So maybe go back to this example where we had 3 dimensions. Don't know where it was. Here, kind of imagine we don't have 3 dimensions, but 10 dimensions. It's impossible to see anything here. So maybe we want to just visualize the data in some way. And that's where Matplotlib comes into play. Matplotlib does not only work with NumPy, but also with kind of pandas, what we're going to learn about later. But just let's create kind of very simple example. Let's create an array that's supposed to show us the electricity demand data for 6 different hours, just a few random values. So we have one array for the actual values and one array for the position. And we can call the function from this PLT alias that we imported at the beginning, and say we want to plot the hours against the demand. And then it would look just like that. Of course, this is very basic. It doesn't have any axis labels. It didn't have any choice about the colors. They're just some defaults. And in many cases, we of course want to adjust that. At the bare minimum, we want to add some labels to that. And this is maybe something I will not go through kind of step by step, but there are a few links here where there's a range of different markers that you can choose, a range of different colors that you can choose that are predefined and so on. That's really a matter of taste, but here are just the basic things that we can change. So take this, for example. This was kind of our previous command. And this function, plot, it takes a range of different arguments. For example, we can say there should be markers. And let me just go through that maybe step by step. So if I add the markers, I get some points where our data points are and where kind of some interpolation happens. I can specify that the line style should be dashed, for example. That works. There's different options. I could also just say dotted. And I can maybe specify that the color should be orange and the label should be demand. So the color orange shows up immediately, but the label demand, it doesn't. The label demand, it requires me to call another function, PLT legend, which says I want to add some legend to this figure. And in this case, I just get a legend. So far, so good. Let me just make this a little bit smaller so that we can actually see all of it. So what else is really important is that we have labels on the x-axis, labels on the y-axis to get hours and electricity demand in megawatts. If we want, we can also add a title. And one kind of other critical point, our axis is not starting at 0. It's actually good practice to have the axis start at 0. So maybe, let's say, I use the ylim function to make our plot go from 0 to 500, and then it looks much different. Maybe it's hard to see what the orientation here or what the exact numbers are. So maybe a kind of a grid helps for a bit of orientation. So there's like hundreds, if not thousands, of different options. You can choose to tweak kind of the appearance of your plots. But the basic things you can do through these basic PLT functions, like setting X label, Y label, title, and kind of extent of the different axes. Could also be an xlim if you wanted to stretch the x-axis here. So the default here would be kind of like a scatter plot, which is connected by lines. So line plot. There are also different types of plots. You can do pie charts in Matplotlib, but I think one other of the very common plots is kind of a bar chart. So instead of plt.plot, you can say plt.bar. The rest is pretty similar. The kind of the label, setting the labels and so on is also exactly the same. The only thing you really change here is the bar. And that will give you just a bar chart instead. And yeah, suppose that we want to create some or show some relationship, say between electricity demand and temperature data. So I created here some dummy data of that as well. You can also use the scatter function. So there's line, scatter, bar, a couple of other ones as well. And plot defaults to a line chart. So this would look like that you have here the temperatures on the x-axis and the electricity demand on the y-axis. So in this example, it's positively correlated. Not that it does say anything. Okay, that was easy, I would say, because it's one-dimensional data, or at the most, kind of we have one dependent variable. So what do we do with two-dimensional plots? What if we have kind of data that depends on two variables, for example, latitude and longitude? So that in this case, it's kind of two-dimensional already. And there are kind of two main functions that we can use to create kind of a basic plot. So the first function is the so-called mesh grid function that just takes kind of, say we have two dimensions, x and y, the hours and the temperatures. Then our first dimension, we have a list for the values in the first dimension, a list of values in the second dimension, coordinates basically. And we want to create kind of a combination of the two so that we actually have a comprehensive list of all possible points of all possible combinations between values in x and values in y. So the x-axis shape would be just a kind of 50 by 100 array, and the y would be exactly the same. The y would just represent the y values at the respective x values. This we can use to write out just a random function. So kind of, yeah, it's really random. It's just kind of supposed to mirror a PV output, but it's just, if we look at this output, the point is that it's an array with a shape 50 by 100, exactly the same as the mesh grid. So we have kind of, for each of the 50 times 100 values, we have one x coordinate, one y coordinate, and one value. And this we can plot with the p-color mesh function, where we just give the first set of coordinates, the second set of coordinates, and the output. All of them have the same shape. And then we can specify also, we can tweak the appearance. For example, take a specific color map, a different kind of specific set of colors, and then add the usual labels. So let's maybe go like this. So here you can see kind of when the temperature is high, you have maybe a little bit more solar output than when the temperature is low. But what do these values now represent? For that, we also need some form of legend. And there's a function, of course, that lets you add a legend for this color bar. It's called color bar, where you can give this a label as well. But the important thing is what will show up now, I think on the right-hand side, is that you can get just kind of, an index of which colors correspond to which values. Okay, so you might have seen, you might have noticed that we didn't specify anything about the kind of size of the figure or the kind of background color, or we really just worked with the data that is shown and the concrete axis labels. But for example, you may have seen plots where you have two plots side by side that share the same y-axis, for example. So there's some structure to Matplotlib as well, two main data types as well, or classes, the so-called figures and axes. Kind of the figure is kind of the canvas of the whole. Yeah, it's like a canvas where you can put things, and then individual elements. So this could be an individual element. They can be arranged on that canvas. It's kind of a bit like a hierarchical structure. Kind of figures sit on top, and then you can add axes to those figures. And the way it could look like, well, what you get if you create an empty figure with a so-called subplots figure, you can get kind of a figure object out of it and the concrete axis that it creates. And this just creates an empty axis, and this, we can say, onto this axis, we want to plot some values and some other values, and they will end up in the same figure. And then this is kind of a very basic example where your subplots, actually there's only one subplot, but this function, it takes arguments where you can say, I want subplots, one row, one column, no, one row, two columns, and this should have a certain size. It should have a certain size in the x direction. That would be the first value. So 10 steps in the x direction, 4 steps in the y direction, and the y-axis should be shared. So let's just see how that should look like. So then you get kind of a prepared plot of a prepared figure of 2 axes, and then we can access axis 1 by its index 0. So kind of this axis here is kind of like a list. You can say we want to access the first one, a bit like any other kind of NumPy dictionary or list, and plot some random data there. Oh. So we put that on the left. And could plot something else on the second one. And you might notice that, wait, we don't have any values given on the second one. Well, it's because we said share y is true. So this 24 corresponds to this tick here. We can remove, so why is that valuable? Because if we remove this share y, then we get kind of 2 differently set up axes. And it's actually hard to compare the values there because the points of reference are different. So that's, if you do side-by-side comparisons and the values are comparable, then it's maybe a better idea to do share y. And then we can, instead of using PLT title, we can control the titles of particular axes with slightly different syntax. So for example, we can say axes 0 dot set title. So the equivalent would have been PLT title, but this wouldn't work because it's not specific enough, because it doesn't know where to put this title. So we can put the titles separately for each of the axes. Yeah, and then we get the 2 separate titles on the axes inside one big figure. Yes. Okay, yeah. So let's start from a base case where we don't have that. Then the Matplotlib will have some way to auto-size the axes. It will look at, okay, for the values that you want to plot, what range do they have? So smallest value will have 15, the biggest value has 22, and here is 10 and 24. It's different, fair enough. And then it will just maybe have some kind of margin around it and say, okay, kind of plus 5% of this range I add to either end. But the problem here is that if we actually want to say it's both electricity demands and it's country A, country B, then this can visually create the wrong impression because the kind of points of reference are not the same. A value that is here on the same kind of level represents 24.5 in the one plot and 22 in the other. And of course, we could correct for that by saying, okay, actually, we want this one to go from 0 to 30, and this one also from 0 to 30. Then we have kind of a common point of reference on the y-axis, and we can kind of compare the slopes and things like that on the between both plots. And this is already good. Sometimes for saving some space, I mean, this is duplicate information of information that we have here. So you can also just say share y to, and that just removes the second kind of the duplicate information.